Okay, to finish up this introduction to orbits, I want to prove this result, which relates the size of orbits to the index of stabilizers. And let me just look back here at one of these examples that we did. In particular, I want to look back at the calculation that we did where we looked at S4 acting on itself by conjugation. And we looked here at the size of the orbits, which were the sizes of the various conjugacy classes. And let's look, for example, at this calculation here. The orbit of the transposition 1, 2 had 6 elements. And the stabilizer of the element 1, 2 had 4 elements. And S4 has 24 elements, and 6 times 4 is 24. So if the order of the stabilizer is 4, its index is 6, which is the same as the size of the orbit. And similarly, if you look at this case, the orbit of 1, 2, 3, this was the collection of 3 cycles, had 8 elements. And the stabilizer of that element was a subgroup of order 3 and therefore index 8. So again, the index of the stabilizer subgroup and the number of elements in the order was the same. And this is the fact that I want to prove holds in general. So the proposition is that at least if the group G and the set X are finite, then the index of the stabilizer of X and the size of the orbit of X are the same. But more generally, we can do a little bit better. There's a bijection between the cosets of the stabilizer are bijective in one-to-one correspondence with the elements of the orbit of X. And the proof of this is to consider the following function. So we pick an X in X, and we consider the map which takes G to X just by sending an element of G to where you get to if you apply G to X. So if you want a sort of a little picture of this, we start at X. X is fixed in this calculation. And now we start applying G to it for all the different possible elements of G. And we see where we end up. And by definition, the image of this map is the orbit of X. Because what is the orbit of X? It's everything you can get to by applying G to it. So you're in the image of this map if you're of the form Gx, and that's precisely the orbit. It's the equivalence class of things which are G equivalent to X. So Px is the image of Px is the orbit of X. Now, what else do we know? Well, we know that if you happen to be in the stabilizer and you apply Px to it, then you just get X again. So let's define our correspondence, right? I want to give a correspondence between cosets of the stabilizer and elements of the orbit. So I want to define my correspondence is going to be the following. Let's call this P twiddle. And it's going to take me from the cosets of the left cosets of H of Gx in G to the orbit of X in X. And it's going to be the following map. P twiddle of Gx, the coset, is Gx. So let's think about this a little bit. I have to first check that this is a well-defined map, because as we know, there are lots of choices for the representative of a coset. And here what I'm really saying is pick any representative of the coset and apply it to X, and you'll get the same answer. But that's actually true, because suppose I take G1 in G times Gx, then G1 is G times H, where H fixes X. It's in Gx, right? The difference between two elements in the same coset are that they differ by right multiplication by an element of the subgroup. And G1x is GHX, but HX is X because H is in the stabilizer. So this map makes sense because no matter what representative I pick for the coset GX of GX, all those different coset representatives differ on the right by something which doesn't move X anyway. So when I apply any one of those elements to X, I get the same answer. So this gives a well-defined map. Now we have to prove that it's surjective and injective. Well, it's surjective because take any element if X prime is in the orbit of X, then X prime is equal to Gx for some G. And so P twiddle of GGX is Gx, which is X prime. So this map is onto the orbit. The interesting part is the injectivity. So suppose that P twiddle of GGX equals P twiddle, let's call this G1, equals P. This is the usual thing of trying to check injectivity. So here I proved that it's surjective. To prove that it's injective, well, we just calculate. What is this telling us? This is saying that G1x equals G2x. But if that's the case, then that means that G2 inverse G1x equals X. And that means that G2 inverse G1 is in the stabilizer of X. And that means that G1 is in G2 Gx. In other words, these two cosets are the same. And that proves injectivity. So this is kind of a magical result, because not only does it tell you that that the number, if you want to know how many elements there are in the orbit of a point, it's enough to know the index of the stabilizer of an element. But it also actually tells you that you can recover the action of the group on an orbit by looking at the action on the cosets. I'm not going to use that so much, but maybe just to wrap this up, let's go back to our D4 example and just see if this has any chance of being believable. So remember D4 acting on the square. And remember we showed there's just one orbit. So in that case, D4, for instance, if we call this 1, D4 times 1 is the full set, 1, 2, 3, 4. D4 has order 8. This orbit has 4 elements. So it better be the case that the stabilizer has 2 elements. And in fact, it does. Remember, we saw that the stabilizer was the stabilizer of 1 was the subgroup generated by this reflection. So it was a 2-element subgroup E and the reflection 2, 4. So it all fits together. The stabilizer has 2 elements, the orbit has 4 elements, the group has 8 elements. And we already saw in the case of the symmetric group S4 that the stabilizers, that in the cases that we worked out for the conjugacy classes, that the number of elements in the conjugacy class and the index of the stabilizer have to be the same. So let's stop there for now.